In the last video, we took a look at Newton's second law, and now what we're going to do is integrate Newton's second and third laws while exploring contact forces. So the first system I want to study is what's called Atwoods Machine. It's not much of a machine, but it turns out to be a very useful example that you can solve by many different techniques. So we'll probably be seeing this again. It's just a couple of weights hanging over a pulley. So let's put, this is my mass M1 here. Let's make a bigger mass here, M2. And we'll make this one, say, 0.1 kilograms, and this one here, 0.2 kilograms. Now, if we know from our common sense, if we let these weights go, this one's going to accelerate up, and this one's going to accelerate down. And in fact, the magnitudes of the accelerations will be equal. And this is because we're assuming that the string doesn't stretch. So however much one mass is moving, the other mass has to move exactly the same to keep the length of the string the same. So what I'm interested in finding is what is the magnitude of the acceleration of the blocks, and also what is the tension in the string. So when you're solving a problem like this, first thing you want to do is identify how many unknowns do I have. In this case, 2 that I'm solving for. And then you realize that you're going to need at least as many equations as you do unknowns. And so in this case, your instinct would be to go and use Newton's second law of motion. And that would be a correct instinct. But here's the deal. When I go ahead and make a force identification diagram for this guy here, the forces I have are gravity, we'll call that Fg1, and tension. And when I go and draw a free body diagram for system number 1, like so, the force of gravity acts straight down, and the force due to tension acts straight up. Well, at best, that's going to give us one equation because nothing's happening in the x direction. So that means we need another equation. For that, we need to pick another free body in the problem. In this case, our mass M2. You can go ahead and draw a free body diagram for that mass as well. And again, we will have the tension due to the force due to tension string acting up, and the force of gravity acting down. Now, whenever you're doing more than one free body, you want to go and take a look, see if you can identify any third law pairs, or, as a lot of textbooks tortuously put it, pairs of forces that act as if they are third law pairs. And the answer is yes, you've got this here. And you might say, wait a minute, sure, they're equal, they're the same kind of force, but they're not opposite. And that's why the whole phrase, as if they were a third law pair. So pardon me for just a quick second while I go into the weeds of how this works. It's not a big deal if you can't reproduce the argument, but just so you know what's really going on, and if anyone can ever come up with a better name for this, I'm all ears anyway. So what I'm going to do is I'm going to just imagine that there's only a handful of molecules in the string going around. Now in practice, there'd be like 10 to the 23rd or so molecules going around the string, but that doesn't change the analysis. So there will be our force due to tension here acting on the string, acting on this molecule. And what's keeping that molecule, let me make that force arrow smaller. So there'll be a force due to tension acting like so. And then angled off, there'll be another one pointing toward that guy there. And these will be the same because they're the same bonds all getting stretched. And then there will be a normal force from the pulley acting on it. So these two, so the way it works out is that when you add these up as vector sums, these two are equal via the second law. Okay, now if I go and turn my attention to that molecule there, I'm going to have to just draw it off to the side a bit. It will feel a force due to tension from the molecule down into its right, and that's a third law pair right there. And then it's going to feel a force due to tension from the molecule up into its left. And again, there will be a normal force from the pulley pointing like so. And again, these will be equal via the second law. So as we go around the pulley, what you have is all of these tensions that are equal via a combination of second law and third law pairs working their way around the pulley. All these forces due to tension are equal until you get all the way over here where this force due to tension is equal in magnitude to that force due to tension. So it's this very long-winded combination of second and third law pairs working molecule by molecule around the pulley. I am all ears if anyone can ever come up with a better name for that, but the phrase often used is pairs of forces that act as if they are third law pairs. So the tension here is just such an example. We know that they're numerically equal, but it's not merely because of the second law, but because of the third law, but because of this very long-winded combination of second and third law pairs working their way around the pulley. Alrighty then. So let's go ahead and express Newton's second law of motion for each of these. Now, when you are solving second law problems, you want to cleverly choose your coordinate system, and for each free body you are allowed to make a different choice of coordinate system. And in the absence of anything in a problem that tells you otherwise, my usual recommendation is to point the coordinate system to match the acceleration of the object. That will make the components of acceleration positive and just slightly less room for error in setting up a problem, at least in my opinion. So now let's go ahead, with that set aside, let's now go ahead and write Newton's second law for the first mass. So this one will say that F net on object 1 equals M1A. And, oops, that should be object 1. There we go. And so that'll be T plus FG1. Again, we're adding the vectors here, equals M1A. Now we'll go ahead and take the Y component of that. And here, because the acceleration is up, I'm going to choose the Y components to be up. Or vertical. The positive Y to be up. So the tension is pointing straight up. So there's no horizontal component. So it's all vertical. So all you're left to do to pick the components, figure out plus or minus. Since it's acting in the positive direction, it's plus. Then for gravity, it's, again, acting entirely vertically. There's no horizontal component. So all we have to do is pick a plus or minus. In this case, it's acting in the negative direction. So we would write minus FG1 equals M1. And we, again, take a look at our acceleration. It's acting up. We chose up to be positive, literally for this reason. So I can just write M1A. Okay, now let's go ahead and do our second free body here. So this is going to be, Fnet on object 2 equals M2A. And again, same deal, we'll be writing as a vector T plus FG2 equals M2A as a vector. Then we'll take the y component of that. And again, same logic. Everything's vertical, so you just have to pick plus and minuses, but now we have to be careful. The tension now is acting in the negative y direction because we chose plus to be down. So I have to write minus t, and FG2 is acting in the positive y direction again because I chose that to be down. So FG2, and I made that choice because I want, since A here is pointing down, I wanted A to be positive. So M2A. All right, well, we're well on our way here. So now that we've got it all set up and we've identified our tools, now we're just cranking on the answer. So we're just going to be doing some algebra for a bit here. So we've got two equations and two unknowns. Our unknowns are A and T. And there are many ways that you can eliminate the tension between these two to get A, which is where I'm going to go first. So, pardon me here. My bad. So, you can say, for instance, solve both of these for the tension and equate. You could solve one of them for the tension, stick into the other. But I'll just show you a trick that doesn't get a whole lot of love anymore, but it's kind of useful for this one. And that is, you can just add the equations, right? T minus FG1 equals M1A. And I will add to that the equation negative T plus FG2 equals M2A. So I'm just adding the two equations together. So when I add the two equations together, I'll have T plus negative T is 0. And then I'm left with, what's left? FG2 minus FG1 equals M2A plus M1A. All right, and we can remember that FG2 is M2G minus M1G equals M2A plus M1A. And we're almost there. I'm just doing a little bit of grouping action at this point. I can pull out a G from both of these terms. So this will be M2 minus M1G. This will be M2 plus M1A. So we get the acceleration is M2 minus M1 over M2 plus M1G. So this will be 0.2 kilograms minus 0.1 kilograms over 0.2 kilograms plus 0.1 kilograms times 9.8 newtons per kilogram. And then we can just note that since we're going for an acceleration here, a newton per kilogram is dimensionally the same thing as an acceleration. So what we get is that it's going to be 1/3 G. So we will get that it is 3.27 meters per second squared. All right, now if I want to go back and get the tension, I can use either of these equations. So Sure, that one. So if I take that one, T minus FG1 equals M1A, I'll get that T is equal to FG1 plus M1A, which will be M1G plus M1A. And again, I can group M1A plus G. So this will be 0.1 kilograms times our 3.27 meters per second squared plus our 9.8 newtons per kilogram. When I multiply either of these by kilograms, I will get newtons. So I will get 1.31 newtons. And that makes some sense. The force of gravity on M1 would be 0.98 newtons all by itself, and since it's accelerating upward, that needs to be bigger than 0.98. And by the same token, the force of gravity on M2 would be 1.96 newtons. And since it needs to accelerate downward, the force due to tension needs to be less. All right, so that was our example there using tension. In the next one, I will bring in the normal force and friction. So I'll catch you in the next video.